This is a color session again, the second one in the series, which means that I'm not doing it. Luckily, we have Michiel here who gets the mic from me now and is in charge for the next, we'll see, 45 minutes. We'll see how long it takes.
Okay, welcome everybody. As David says, this is a color session. This time we're going to talk about how to communicate about color. Now, if you were here 2 weeks ago in our previous session, you know that back then we talked about gamma radiation, rainbows, cosmic rays, and apples, I believe. Today, we're going to continue that story. So let's have a brief, really quick recap of the last session. If you missed it, no problem. Also, like David said, these sessions are recorded and they are on YouTube. Feel free to go watch the previous session after this one, and then you can catch up with what you missed last time. Last time we talked about lights. Specifically, we like to talk about standardized light sources, for example, D50, and we talked about the spectral power distribution curves that describe which wavelengths of electromagnetic radiation are present in our light source. Then we had a look at objects, and for our objects, I had an apple, I had my phone case, and we know that those also have a spectral reflectance curve. So for those objects, we have a different curve. And then we talked about the human element. We talked about the person watching and interpreting the light. And we found out that there are color matching functions that describe the human visual response to those specific wavelengths. And all of this gave us a numerical, a mathematical way to interpret light. So now that we have that, now that we are able to change light into color, and we have a way of determining what color a certain combination of wavelengths of light is, we have to discuss how we communicate that to each other. So today, communication is key. Let's have a look here. We have a person, and we have two patches of color. These are two patches of yellow, and one of them is our four-piece branding yellow. The other one is not. Now, how do we talk about this color? Well, we can call it yellow. Humans are really good at determining when colors are different when we put them side by side like this. I don't know how Zoom is translating this to your screen, but there is a slight difference between these two patches. And you can probably tell just by looking at it. Now, let's say that you're looking at one of these patches while the sun is out, while it's very nice weather, and you see one of these patches. And you only get to see the second patch when it's cloudy. If you don't see them together, would you be able to say that that is a different color? It's quite unlikely. Now, let's say that you look at one of these patches in the morning, and you get to see the second color in the evening. Some time has passed, you get tired, and you see the second patch. Would you be able to say that the colors were different, or would they just both be yellow? Would you be able to tell the difference? Probably not. Let's say you print an artwork today and you print the same artwork tomorrow. Would you be able to say that the result is the same? I doubt it. And then, of course, there are differences between people. Specifically, there is this old joke that I come across on the internet every once in a while, that women and men have a different way of describing colors. Where men typically describe it in some major factions, like the rainbow colors, women have a lot of names. That's typically the joke. Of course, there are definitely men who can describe multiple shades of purple, right, David? So this is typically what we get to see. Now, one color, for example, the one way we can describe colors is by giving them names. Another way to define colors is to use those curves that we had before. So you remember my phone case, right? My phone case is this color, if you can see my camera. That was the spectral reflectance curve of my phone case. Now let's say that I lose that phone case. And I really liked it. And I really liked it being that color. And I have to ask someone else to buy me a new phone case that has the same color. I could tell them, hey, you know, I want that phone case, and I can send them the curve. I can send them this curve, and I can say, I want it to be this color, right? But that's a difficult way of communicating, because you would have to interpret that curve. You would have to think about it. I would have to send you an Excel file to describe a color. That's a bit weird. And how would I even get that curve if I haven't measured it already? I would have to measure a color and do all the maths and do all the stuff to get the description of a color. So that's a bit annoying. Then a different way of talking about it is I could describe the color with a name. I could say, I want this teal phone case. I want the cyan phone case. And that would already help. But maybe they have multiple options. There is this color that is in Flemish, it's called appelblauwzeegroen, which to English translates apple blue sea green. Now, what color do you think of if you get that name? I Googled it. This is what I get when I Google the color. Now you see the results are varied, right? If I take patches from this, I have these 5 patches really easily that are different colors on that page. Now these 5 colors, they are wildly different. I couldn't print one of these colors for a job, for a client, and then the next week print another one of those and say, hey, this is the same color you asked for. I couldn't do that, it's way too different. So another way to do it is name them more specifically. We could use a naming system. For example, I might like this Robin's Egg Blue color that's been made by Crayola. Apparently that's been a Crayola color since 1993, which is longer than I have been alive. So that's definitely a way to define a color that is really static. That's this crayon, by the way. So I could say, I want the phone case that is Robin's Egg Blue. And that would already be way more specific than just using teal, because Robin's Egg Blue has been defined by Crayola to mean this exact thing. And if I buy this Trolls set of Crayola crayons, and I have someone else in America have this set of crayons, and I tell them to get me something in the color Robin's Egg Blue, they would be able to have the exact same color. That's one way to talk about color, by defining them very specifically. Now, that's pretty much exactly what Pantone does, right? Everybody here has seen one of these Pantone books. They have a whole list of patches, and they name them by giving them a number. And if I have the Pantone book and I say my color that I want to have is Pantone number this much, for example, a yellow could be 106, and I tell someone else to use that color, then they can use the exact same color. Of course, as long as they use an up-to-date Pantone book that hasn't been lying in the sun for this long, or they use the digital values associated with it. That's called a color naming system. That's one way to describe color, by giving it proper names. Now, a different way is by using attributes. Of course, the attributes we know best are the hue, saturation, and lightness. These are the 3 attributes with which you can describe any color. Hue being the primary tone of the color, the actual color, the red, green, blue that we use. Saturation being how strong the color is. So less saturation would be a more neutral, a more gray color. And lightness being how bright the color is, going from black to white, but that's basically a neutral axis. Now that's a 3D space. So if we take this axis and we put it aside for a second, I can open up this 3D object. That's a 3D space that has those 3 attributes. Hue is going around the circumference of the object. The lightness is the neutral axis in the center. So if I take my laser pointer, that's the axis that is over here. That's white to black, to top to bottom. And the saturation is going away from the center. And we can use these 3 attributes. Now, this might look a bit familiar to you, because last time we also talked about these color mixing. And if you look at this, you can see that if I roll this along this axis, it gives us the same information. The outsides of this color mixing the primaries, gives us the same view as the top view of this object would look like. So this way we describe it by attributes. Now, of course, you can use those numbers. We'll look at that in a bit. But there was this guy called Munsell who created a color system based on those attributes and visual differences interpreted by humans. So each of these patches is essentially a named patch that has a certain hue, saturation, and lightness. And you can see the lightness goes up when you go from the bottom to the top, the saturation increases from the center outwards, and the hue changes around the circumference. The cool thing about the Munsell color system is that the distance, the visual distance between two colors, so the difference between two patches that are side by side in any direction, should be the same. That gives us all these patches that have a specific color. The distance is always the same. That's actually worth mentioning this already. Another good reason is that Munsell kind of follows the LAB color space. It's pretty close, except, of course, that here we define it by steps, and the LAB color space is a continuous shape where you can specify any color based on the three values. So, and from that we go from color systems, like the naming systems that we use for Crayola, Pantone, or the system that we have for Munsell, we go into color spaces. And there are different color spaces. Specifically, any object that you, any way of looking at color probably has its own color space. If I look at it on my monitor, if I make an image with my camera, if I browse the internet, or if I look at something that has been printed, each of those ways that color is reproduced has used its own color space, has its own limitations and advantages. The problem is that any monitor is different from each other. Any print, any printer is different from each other. So defining color using those color spaces is not always very interesting, because you might be talking about a different thing if you're talking to someone else. So we have these color spaces that are device independent, that are the same for everybody. And these are typically theoretical color spaces. We'll look at device dependent and device independent color spaces. We'll look at how these interact during the next session. So on May 11th, I believe it is, we will talk about color conversions, about color management in practice, and then we'll discuss this in more detail. For now, I'm going to zoom in on these device-independent color spaces, and we'll look at what's happening here. Now, remember that the last time we talked about these light curves, we talked about our object curves, and about our color matching functions. And from this, using this information, we can calculate the theoretical color space, and we can calculate the XYZ tristimulus values. You basically multiply every wavelength of our object curve with every wavelength of our light curve, with every wavelength of our color matching function, then take the sum of that for our RGB, and then we get our XYZ tristimulus values that identify any color. XYZ is the basic of every CIE color system. From there, we can calculate the YXY color space or the LAB color space that everybody knows and that everybody's been using. So we'll get to these two in a bit. And from LAB, we can go to our delta E, which will eventually tell us the color difference between our yellow patches. So let's take this color matching function and see the results that we get from here. I identified three colors, the red, green, and blue colors here, and I have their XYZ values written next to them. What you see is that, and it makes sense if you look at the curves, the highest X value would mean that the color is more red. If the highest value is the Y, the color would be more green. And if the highest value is the Z, the color would be more blue. Makes sense, because obviously they respond to that color response. Now, even though XYZ is a good way to identify a specific color, it's not the best way to communicate to each other. because these values don't immediately give you an obvious view of what color it is, right? If I tell you my phone case has to be XYZ with these values, you wouldn't know exactly what this describes. This is hard to interpret. I also noted some light sources because, of course, you can also note the color of a light source and not just the reflectance curve of an object. And I have our A, our D50, and our D65 noted here. Now, noteworthy is that when you talk about perfect reflectance or light sources, we will note the Y value as 100. This is just an agreement that's been made to make everything more clear. Now, what we can see is that if my X value is the highest, it's a redder color, makes sense. Here, this is quite neutral. And if we have the D65, we see that the Z is bigger, so the color is bluer. I know this isn't very obvious with those circles, so I increase the size a little bit to hopefully make it more obvious. So now that we have these XYZ values, we calculated those, and we can put those into a new color system, a new color space, actually. This is the YXY chromaticity diagram, a 2D representation of a color space. And you can see the X and Y axes noted here. The capital Y isn't represented on this diagram, so you always have to note that separately to identify the brightness of a color. But you can already identify the color itself. You can see on the edges of the shape, we have the dominant wavelength of each of the color represented, and we have the highest saturation of that color represented. So we see, for example, a color that is on the edge here with a wavelength of 600 nanometers would be a reddish color, and here with 480, it would be a very blue color. Neutral colors occupy the center of the shape, so that's where our white is. We can calculate our X and Y with the formulas we have here on the right, starting from our XYZ color space. And you can see it's not that complex, the formula we have here. So let's take a color, let's do it practically. And I'll take our 4-piece pink. I'll start by measuring that and calculating my XYZ. So I have my XYZ values for that color. And then I can use the formulas at the top and I can calculate my XY values for that color. Now let's mark that on our map. Let's put it on the diagram. So our color is over there, somewhere in the reddish pinkish area. That's perfectly where I expected, because obviously it's a reddish pinkish color. I did the same thing for D50. So I have my XYZ values that we took on the previous slide, and I calculated the X and Y for that, and we can put it on the diagram. And we can see that's where our white is for our D50. Now, one neat trick with the XY diagram is that you can show the primary wavelength for a color, the dominant wavelength for a color, by doing this. If I have my white identified and I have my color, and I draw a straight line through these 2 points, I can see the dominant wavelength. Now, the purple is an unfortunate example for that, because here between these 2 points, we have the purple barrier where no wavelengths are noted. So for any colors that would end up there, like this one, somewhere around here, the opposing wavelength would be noted, and you would mark that with an extra symbol, and then we would have it somewhere around 500. So that's a cool thing that you can do with this diagram. Now, another thing we can do, since we can mark our colors, is we can identify our color spaces. So let's take a copy. And actually, first, let's mark our color spaces. For example, our Adobe RGB. We can mark our 3 primaries, connect them to each other, and this will show us how big, at least in 2D, our color space for Adobe RGB is. We can do the same thing for sRGB, and you can see where the differences lie. So it's mostly in the greenish area, but also a bit of blue and a bit of orange. Now, another thing we can do here, and this is why YXY isn't used a lot, is we can mark our color differences. So let me add some things to the second copy of the diagram. All these ellipses, these are called Macadam ellipses, identify the same color difference from the center of the ellipse to the edge. So that means that a color difference from here to here and the color difference from here to the edge is the same visually for us. And that makes this way of noting color not the best for what we're trying to do. The holy grail of color management systems would be a perceptually uniform color space, where the distance between any two colors gives us a similar value. So if we say that the distance, that the color difference between two spots here is 2 of whatever, then the same distance on the other side should also be 2 for a visual difference. And that's why the y-axis isn't perfect. But we have other color spaces. And in 1976, the LAB color space started being used. Now, you see it's pretty much the same as we had before with our Munsell. We start with our most neutral colors, our white in the center. We have our brightest, our hues around the circumference, and the saturation increases the further you go from the center. Now let's look at that in 3D. So if I put this like that and we add our AB axis, this is our A axis, this is our B axis, we can also add our L axis, which goes black at the bottom and white at the top. Then we have our LAB model. Now our A axis goes from green to red, our B axis goes from blue to yellow, and our L goes black to white and is neutral in the center. LAB is also based on our XYZ values, and differences between the colors in LAB are a lot more uniform. So two differences located like this are a lot more uniform than they would be in the XY diagram. You see, the formulas are a lot more complex. That's because they have to take into account those uniformity issues. They have made adaptations to make this work better. You also see that besides our XY values that we have and our Z value, we also have YN, XN, and ZN on this diagram. And those are the values of our reference white. So that means that our white point is very important for LAB color space because it's part of the color. So if we work with D50, for example, we would have to use a D50 white point as well. Let's again look at a color. So I have my same XYZ values for our 4-piece pink. And I can use the formulas above using D50 white and get an LAB value for that color. Now, a different color space that actually uses the same diagram is LCH. L still for lightness, C this time stands for chroma, and H stands for hue. And we already kind of said what that is, right? The hue is our circumference, and the chroma is the distance from the center, the saturation. So in this case, we're not using a grid, like with this color space, we're using a grid, right? We're going around 2 axes, 3 axes. So we're using a 3-dimensional grid to locate any color. With our LCH color space, we're using angular polar dimensions. So if I use, for example, a red color and I change the color because I wanted it to be a bit further from the axes, I have LAB values for that red color. Then I can mark that color because I already know where it is. And I can see that this is the distance from the center. So the distance from the center would indicate my chroma. And then we have the angle around the axis starting from 0, which is this line, and we see the hue. So I can mark that and I can say our L is 54. I can't indicate that here because it's a bit hard to draw on this 3D model when you're looking at a 2D space. I have the C, which is the distance from the center, and I have the H, which is the hue, which is this angle. And that's a different way of noting color in the same LAB space. Now, this is actually progressing quite quickly.
Is it only a mathematical transformation between LAB and LCH? I mean, another way of noting, or is there also a fundamental difference in what is used?
It's calculated differently, but I think I might not have noted no, I have not noted the formulas, but you can calculate it as well. But it's really just a different way of noting. It's using different primaries, not really primaries, attributes, right? With LAB, we're placing it in our 3D space based on a grid. With LCH, we're using our light attributes, our color attributes to identify a color. So they have a different use in that manner. LCH is actually a bit more understandable to talk about than LAB is, because if you talk about LAB, then you have to already understand that the A-axis goes from red to green, the B goes from blue to yellow. You have to take into account that you have a positive and a negative in LAB, because we start with an origin point 0. So you have to know that you go positive and negative. So it's still a bit difficult to understand here, but they're easy to work with for calculations, while LCH is easier to understand, but it basically ends there.
But in LCH, if I understand well, if you just wanted to move from the center to the outside, yeah, so basically change the chroma, then in LCH, I only have to change one value, the other two would remain.
Yeah, if you want to decrease the chroma, decrease the saturation, you would only change the C value.
Yeah.
And if you would change the L value, you would decrease the lightness. While with LAB, you would have to change both the A and the B to decrease the saturation.
Okay. Okay.
Yeah.
And
so
if you want colors that are the same chroma but you just want different hues, it would be the same thing. You just change one value.
You change the angle. Yeah, you change the hue angle.
Yeah.
And the hue angle starts at the right and then goes counterclockwise around the shape. And yeah, so basically 90 degrees gives you yellow, 180 gives you green, and so on.
And I don't want to get ahead of you, but can you calculate? So are there mathematical formulas to go from LAB to LCH and back?
I think so, yes, but I haven't noted them on the slide, so I can't show them to you. I would have to update my slide deck again to add that as well.
No, but so what I'm thinking of is that would mean that if you have a color in LAB, you can transform it to LCH, do the meaningful change, and then calculate it back to LAB. That would be possible.
Yeah, it's definitely possible, because either way, they both relate to XYZ. Yeah. So you can always go with the XYZ conversion back and forth.
Yeah.
So now that we covered essentially 50 years of color theorem and research, we can go back to our original slide, and we can have our two yellow patches here. Now the question remains the same, right? If I have these two patches, how would you say they relate to each other? Would you say, oh, these are actually pretty close to each other, I guess? Would you say, oh, this one is a bit greener, this one is good enough? Or someone else might say, oh, that's miles apart, that's not even close to each other, what are you talking about? So even though we now are able to take our color, measure our color, and put it with exact coordinates in a 3D color space, we're still not much closer in our communicative aspect of it. We can now tell each other, oh, I want something with the color LAB values these, and you can communicate that to someone, and you can say, my brand color is LAB this, and you will be talking about the same thing, sure. But if you have two patches, and we talk about these two patches, we might need something else. We might need to have something to identify the difference between those colors, to say what is acceptable and what is not acceptable, what is too different. So let's take our good enough and let's determine what is good enough. If I take my two patches and I calculate the LAB value for those patches, so I measure them, I get my spectral reflection values, I calculate the XYZ from those values, and then I calculate the LAB from those XYZ values, then I get the following LAB values for my two patches. Now, we've just saw how LAB is built. So let's look at these values. We see that the L value here is a bit lower. So this color is a bit darker. We see the A value is more in the negative, which makes it greener. And we see that the B value is less, which makes it bluer. Okay, that gives us some information that this color is different in this way. Cool. But we still don't know how different they are. And for that, there's a formula. So here is the delta E76 formula. Now, you might immediately notice this is basically a three-dimensional version of the Pythagorean theorem. You're basically calculating a diagonal distance between three axes. So it makes sense to use something like this. Let's take that formula and fill in the values we have for our two patches here. You can see I've added all of those. And then we can calculate the result from that. And we see that delta E is 5.59. Now, typically, 5.59, I would not consider close enough. I would say that difference is too big. A delta E of 1 is defined as a just noticeable difference. It's where someone with a bit of experience would say these colors aren't the same anymore. A delta E of 2 is what is typically accepted as a brand color requirement. If you're printing brand colors, for example, for Coca-Cola, and you have a bigger difference than a delta E of 2, it wouldn't be good enough for them, because then people start seeing that it's actually a different color. Delta E of 3 is typically acceptable for any commercial print. And then depending on what what work you do, who you talk with, who your customers are, you might define a different delta E. And in some markets, you might say delta E of 5 is fine. A delta E of 0 is impossible. It's just because even when you take two measurements of the same patch on the same place right after each other, the slightest difference in how that spectrophotometer measures those values already gives you a difference. So 0.00 won't happen. Now, David, did you want to interrupt? You're muted though.
I have to say this because I'm a physicist. So measuring is fine, but you need to tell what the measurement uncertainty is or limitation is when you talk about this as well, right? So I'm glad you say that 0 is impossible. Is it really starting to be meaningful if it's only one difference? Is the measurement typically that good? That's
a good question. I reckon that's going to be device dependent. That's going to, like, typically you have three ways of looking at how good a device is. You can take your device and you can measure the same patch 5 times,
yes,
and you can see what the deviation is. And that's your inter-instruments difference that you have. How good is my difference in stability? Then you can take multiple devices. You can measure the same patch with all of these devices, and you can look at all the measurements that you get. And then you get your instruments, the difference between different instruments. And you can say, oh, well, look, some of these measure a different value. Which one is correct? Well, who knows, right? So you have those differences. And yeah, you also have, of course, the age of the spectrometer. It might get different over time. You have to make sure that you calibrate it correctly. So usually with a spectro, you have this white patch included to calibrate it, to make sure that you always get a stable calibration for your device. But yeah.
But if you're calculating, if you're calculating a delta E for one patch, then the only thing you really need to look at is the measurement uncertainty in that one device that you're working with, correct?
Yeah. Yeah, you can say, okay, so, but like you say, is a delta E of 1 still reliable? If you say that, then there's going to be that discussion for any kind of delta E. You can say, oh, look, my color is a delta E of 5.6, but maybe my device isn't that great, and it's actually less than 5, so my print is acceptable, right? Yeah. And you can start that discussion. So you have to kind of draw the line somewhere, and we'll agree that a properly calibrated spectrophotometer that is in good state will give us an accurate measurement that you can work with. Typically, when I go to create color profiles for customers, I take a very large patch set. So I take like 3,000 patches, I print it twice or 3 times, I measure all of those, and I average it.
Yeah.
And that way, you definitely have something you can sort of rely upon instead of just taking 70 patches, measuring them once, and saying, "Hey, this is fine, right?"
Yeah, because you average out already the mistake you make in the device itself.
Yeah, you average out that deviation by the amount of times you measure your patch, so it helps.
Okay.
But this thing still isn't completely good, this calculation, because it's too simple. After all, our LAB isn't perfect. It's better than XY was in our color differences that we have, but it's not perfect. There are still some differences there, and it's mostly the human's problem. It's us that is the problem there. After all, humans are very good at finding differences in neutral colors. So if we have a color very near our neutral axis, we'll see the difference a lot sooner than we will when it's a fully saturated color. Also, humans notice differences in blues better than we do in yellows. So in yellow, we can actually have a bigger difference before it becomes important. And these things made the creation of the delta E2000 formula happen. So if I move that aside, this is the delta E2000 formula. That's a lot more complicated. Now, most of these things are those changes. They're the changes to account for the fact that the further you get from the center, the less important the difference is. It accounts for the fact that the blue and yellow is a different importance. So that's the biggest stuff there. Now let's recalculate our color difference from our two yellows. And we get a delta E of 2.9. So now our color difference is acceptable. And that's just because they're yellows. If this was a blue, then the difference would be closer to the one we have with the delta E76. So now the print is acceptable. And this again comes to show that when communicating about all this stuff, you have to be very accurate in what you say. So if I say that the delta E of 3 is acceptable, I have to specify a delta E of 3, delta E2000. I can't just say delta E because typically delta E is about the 76 variant. So even that now that we have all this communication, it's still important that we stay detailed and that we stay accurate in everything we say. So to sort of conclude today's whole session, names and numbers. In the end, it doesn't really matter that much which kind of all these systems you pick, as long as the other person uses the same system. If I say I want a color that is Robin's Egg Blue and I use Crayola, then you can't go to the dollar store and buy a crayon set and pick a color that someone else created and called it the same, because it's not the same color. If I use a Pantone book that is new, or I rely on the LAB values that are defined for all these colors, then you can't open put your Pantone book on your windowsill for 5 months during the summer, then grab it and then say this is the right color, because it's not. It will have aged. So within these communications, it remains important that you talk about the same thing. And that's why we have these standards. That's why we have the LAB standard. We can talk to each other using the same reference, and that way define the same color. And that's kind of where we end up for today's session. So next time, now that we are able to define our colors and to go from our spectral reflectance curves for each object all the way to an LAB definition for a color, to an LAB value for our colors, we are getting somewhere. We can use this information where we have a numerical value that identifies each color to translate between different machines. We can say, if I want to reproduce this kind of color in this color space, and I can translate that to LAB because I can measure it, then I can use that same calculation to translate the other direction to a different color space. And we'll talk about all of that in the next session, which is about practical implementation of color management, about profiling, and about different kinds of color management flows. That's on May 11th. I believe that is a Tuesday instead of a Thursday, because the Thursday falls on a holiday. So if you have this as a standard thing on your calendar, make sure that you move it to Tuesday for that week. Before that, though, there is another cafe in between next week about rep-to-print systems and MIS systems. For example, Presero and I believe it's DataLine.
So specifically, the DataLine multipress system in combination with LA and Presero. Yes.
There we go. I'm not hosting that one, so I'm not obliged to know the details yet. I will be paying attention next week. So that was a whole bunch of stuff, and I bet this one was a bit more painful for everybody to watch than the last one because it contained maths and numbers. If anyone has any more questions, we still have a bit of time. I actually kind of hit the mark when David said 45 minutes. So if anyone has any more questions, any comments that you would like to make, because color is typically a field where people have opinions. So if you have an opinion that you would like to share, that you would like to bring up, I'm happy to discuss. And of course, any questions, feel free to, if you don't want to ask them now, feel free to send us an email afterwards and we can answer emails as well.
So there was one internal question about Pantone books, saying if someone has an old Pantone book and you somehow want to choose the color or I guess reproduce the color that you have in there, can you do that?
Measure it.
Yeah.
That's it, right? So you have your old Pantone book, you say, I want this color. Well, you can't use the reference LAB for that color anymore. I think Pantone books actually come with a warranty where they say that it's only valid for a certain amount of time. I'm not sure if it's 6 months or a year, but I think it has a validity period. If it's past that period, then probably the paper has aged, whatever coating they use has aged, the inks have aged, the color is different. So just measure it, have your spectral reflectance, calculate your XYZ, calculate your LAB, and then you have an LAB value you can try to reproduce. Now, I keep saying calculate, calculate. Of course, you won't be the person calculating all that stuff. Every spectrophotometer you buy right now has an automatic calculating stuff happening inside of it. So you make that measurement, and on some of them you even have this little screen at the top, like the TechCon SpectroDance has a little screen at the top that will give you the value you asked for. So if you tell it you want to see LAB, it'll give you LAB on the display. Otherwise, the value, obviously, you will have it inside your color management application. You might have it in an Excel sheet. If you want to have an Excel sheet to calculate delta E's, there is a free resource for that. The CIE actually has that available on their website. So if you just Google delta E calculation spreadsheet, you will find the download for that really easily. And you can enter values and calculate color differences. If you want, all that stuff is stuff that is available to you if you want to work with that.
Then maybe a dangerous question, but if I do that and I either with a Pantone book or something else, I determine that this is the purple I want, and I have the LAB values for it, and put that in Illustrator or whatever, and send that to a printer, am I actually going to get that color, or is that then depending on how good the printer is?
That is a good question. So yes and no and yes. If I measure a color that is simply not printable, right, then you have a problem. And that is possible because the CMYK color space isn't that big. There's lots of colors that aren't there. If I measure a color that I want to display on a screen, you have a better time because RGB color spaces are typically bigger. Now, are you going to get the color you ask for? If on the other side of this, if you use an LAB value and you make it, for example, a spot color that you reference with a specific LAB value, then the other side will see, oh, this is a spot color. The LAB reference for that color is these values. I have to reproduce these. And then we enter the session for next time, where they will have to take that LAB value for that color, and they will have to translate it to whatever device-dependent color space they have for their machine. So I'll give a brief preview, I guess, for next time. If you have your printer doesn't print LAB. Your printer prints amounts of ink in CMYK. But we can print these amounts. We can print X amount of C, X amount of M, X amount of Y, X amount of K. And you can measure that, and you can get the LAB result of that combination of ink. Now, I talked about printer profiling with a lot of patches. If you print enough combinations of quantities of CMYK inks, then you know pretty much how to reproduce each LAB value, because you can measure all of those patches and you know that that amount of CMYK produces that LAB color. Now you put all of those things in a table and you have a big table that says these LAB values correspond to these CMYK values. You do some smart maths on that, because obviously you can't measure every color. You have to interpolate some of the colors with some smart maths. And then if I say I want to reproduce this LAB, I can simply look at that table, I can look it up, and I can say, oh, I have to print this CMYK. And then I can reproduce that color. So that is how the print shop would have to do that. Now the question is, when they do that, is their machine consistent? With a digital press, you're kind of in the clear, because those are pretty consistent. With an offset press, it might depend on how much coffee the guy had in the morning. It's all dependent on how people treat their machines, how consistent their print process is, how consistent their pre-press process is. If they care is also important. There's a bunch of stuff happening there that you have no control over. But after all, now that you know the delta E, you can measure the result. You can say, this is bigger than 2. I don't like you. I'm not going to buy this. And you can go somewhere else.
So kind of the only part that is on my side is I would need to at least pick a color that is in the gamut of whatever I'm going to be printing with or on.
That is your responsibility, yes. Yeah. Or you have to be okay with what happens to it. Yeah. And there are processes where you have a huge gamut, but then you probably pay extra to use that process. So you have to be okay with that. Yeah. And what's also your responsibility is providing the proper description for the color, right? So you have to define it using LAB. You have to say that you want it reproduced within a delta E 2000 of 2. You have to be clear in your expectation. And if you just provide, for example, if I go to Illustrator and I create a color and my Illustrator color space is set up to be a certain thing, and I tell the printer that it was something else, then I'm causing problems because I'm not communicating clearly. So I would have to use embedded color profiles for my Illustrator space, and then they have a proper way to translate that. Or with brand colors, you can use CXF4, which is basically adding what we saw before, the complete spectral reflectance graph for that color inside a spot color file, so that people know exactly what they have to do to reproduce that.
Cool. No more questions that I can see here from anyone.
Okay, then I hope people found it interesting, maybe learned something. That was the goal, right? Having people find this interesting. This will be on YouTube. If I was talking too fast, if you missed something, if you want to rewatch certain parts, rewatch it on YouTube. It will be available. And even then, when you rewatch it and you think of something to ask, just send us an email and we'll answer your questions. Thank you all for coming. I hope to see you on May 11th for the, for now, final chapter of what we have defined as our color webinars. Please check out, if you're interested, the Web to Print and MIS webinar as well. And have a good evening.